So today we will discuss some approximation theorems. We have seen in previous lectures that if I represented by P star the outer measure associated to some measure which is defined in an algebra, and if we have a set, let's say A, whose outer measure is finite and such that the A belongs to the class of measurable sets, then it's always possible to find a set F in the sigma algebra generated by the algebra, such that the set A is contained in F, and the set A has the same measure, outer measure, as F. So this shows that any set which is measurable can be approximated from above by an element of the sigma algebra whose measure is equal to the one of A. Well, today our first result will assert that it's possible to approximate a set A with finite measure if by not elements of the sigma algebra, but by elements of the algebra. So the advantage is that the elements of the algebra are very simple because they are all finite unions of elements of the semi-algebra. But the price to pay in order to approximate this element by sets of the algebra is that you are not able anymore to approximate them exactly, but you pay some error. So the theorem, the first theorem which we want to prove, reads as follows. Well, suppose that you have an algebra of sets of some set omega, and let's say that F is the sigma algebra generated by A. So let's call this sigma algebra by F. Let's assume that we have a measure mu, which is defined on F, and which may take values equal to plus infinity. Let's take a set A in the sigma algebra F, and let's assume that mu of A is finite, and let's fix epsilon positive. Then I claim that there exists a set E in the algebra such that the measure of E minus A plus the measure of A minus E to be smaller than epsilon. So we can approximate the set A in the sigma algebra by a set E in the algebra in such a way that the symmetric difference of E and A, the measure of this symmetric difference, is bounded by epsilon. So this is our first theorem. So let's see the proof of this theorem. So let's fix a set A in the sigma algebra, and let's assume that mu of A is finite. Right? So we have seen in the extension of Carathéodory's theorem that the outer measure of A is given by the infimum over all covers of elements of the algebra. So this is P star of A. It's given by, let me call by nu in this lecture, the measure which is defined on the algebra. So we have here sum of nu of EI, and here the is infimum are taken for elements AI in the algebra such that A is contained in the union of AI. right? And since mu, which is the measure defined on the sigma algebra, it's given by the outer measure restricted to f, this is mu of A, which is finite by assumption. So since it's finite, we can find for a given epsilon, we can always find such a covering which almost reaches the infimum. This means that there exists a covering AI, where I recall AI belongs to the algebra, and A is contained in the union of AI, such that P star of A is the infimum, therefore it's less than or equal to the sum of P no, it's what I represented by nu IA. So P star is smaller of nu IA because P star is given by the infimum, but since P star of A, which is mu of A, it's finite, we can find one which almost reaches this infimum, so that this is smaller than P star of A plus epsilon. Right, so now, since P star of A it's finite, this sum it's finite, therefore there exists n0 such that the sum for I greater or equal to n0 of nu of AI, now this is smaller than epsilon, right? So P star A it's finite, therefore the right hand side here it's finite, which means that this sum it's finite, and therefore we can find an index starting from which the sum it's bounded by epsilon. So now we have our candidate E. So he will be an element of the algebra which approximates A. So E will be defined as the union from 1 up to n0 of AI. Since AI are elements of the algebra, this finite union, it's an element of the algebra. So E, it's an element of the algebra. And now what we need to prove is that P star of E minus A, it's bounded by epsilon, and that P star of A minus epsilon, minus E, it's bounded by epsilon. So we have to prove these two bounds. So let's start from the first one. So P star of E minus A, E is the union from 1 to n0 of AI minus A. Well, but this is certainly contained in the union from I greater or equal to 1 of AI, and therefore by monotonicity of the measure, this is smaller or equal than the P star of the union from 1 to infinity of AI minus A. Now A, it's contained in the union, and P star of A, it's finite by assumption. Therefore, P star of this set, it's less than, or well, it's in fact equal to P star of the union minus P star of A. By subadditivity of the measure P star of the union, it's less than or equal to the sum of P star of AI minus P star of A. And now the sum of P star of AI minus P star of A, it's less than or equal to epsilon by the property here of the family AI, right? So this proves that P star of the union, which is E, so that P star of E minus A is less than or equal to epsilon. So it remains now to prove the second inequality, the second bound. So let me erase this first one and let me go to the second bound. So we want to prove now that P star of A minus E is less than or equal to epsilon. So recall E is the union from 1 up to n0 of AI. Well, but A it's contained in the union. So by monotonicity, this the measure of this set, it's less than or equal the measure of the union from I from 1 to infinity of AI minus the union from 1, let me call J from 1 to n0 of AJ. Right? So here are the points which belong to the union and which do not belong to the first n0 terms. So this set is certainly contained in the set which is the union from J from n0 plus 1 up to infinity of AJ. Right? So this set it's contained in that one because the points in these sets are points which are in the union but which are not in the first n0. So they have to belong in one of the AJ for J greater or equal to n0. Since this set is contained in that one, the measure of that set by monotonicity it's contained on that one. And again by subadditivity, the measure of this set is less than or equal to the sum for J greater or equal to n0 plus 1 of P star of AJ. And again, by our choice of n0, this sum is less than or equal to epsilon, which proves the second inequality. And this concludes the proof of the theorem. Just notation-wise, observe that I'm using sometimes P star, sometimes mu, but mu and P star coincide on the algebra, and mu and P star coincide on the sigma algebra. So you can replace everywhere here if you want P star by mu if you have an element of the sigma algebra, or P star by mu if you have an element of the algebra. So this concludes the proof. So we just prove the following theorems. So if you have a measure defined on sigma algebra which is generated by an algebra, for any set in the sigma algebra which has finite measure, we can always find, for any epsilon, we can find a set in the algebra which approximate the set A in the sigma algebra, in the sense that the measure of the symmetric difference is bounded by epsilon. Well, let me just remark that if the set omega is sigma finite, so if omega is sigma finite with respect to mu, which means that omega can be written as a union, countable union of sets EI, where EI belong to the algebra and mu of EI is finite. So this is, I'm just recalling the definition of sigma finite with respect to mu. In this case, we know that we can extend this measure mu, which is defined in this theorem on the sigma algebra F. We can extend it to the completion of F with respect to mu. Right? We can extend this measure to, so I'm representing here by F bar the completion of completion of the sigma algebra F with respect to the measure mu, and I'm representing by mu bar these completion. Well, what I claim is that the same proof I just presented, shows that in fact you can approximate any set in this sigma algebra by a set of the algebra. So this means that, let me write it, if you fix now an element of the completion, sigma algebra, so F bar, and you fix an epsilon, you can always find a set E in the algebra which has these properties. So that the measure of the symmetric difference, it's bounded by epsilon, and you'll see that exactly the same proof applies. Here I needed an extra assumption that omega is sigma finite with respect to mu, just to guarantee that mu can be extended in a unique way to F bar. So this is why I decided to state this theorem in two pieces, one without this assumption, but in which we just approximate sets in the sigma algebra. Then if you have this extra assumption, we can in fact extend this approximation to sets in the completed sigma algebra. So up to this point, we never used any special property of the set omega. We'll now assume that omega is a topological space, so there are open sets and closed sets, and we will show that we can indeed approximate a set by sets which are open or closed. So let me define first what I will understand by a regular measure. So I'm assuming from now on that omega is a topological space. And I'm representing by B for Borel, the smallest sigma algebra which contains all open sets. And let's say that we have mu, which is defined on sigma algebra F, which contains the so I'm assuming that the sigma algebra F contains the sigma algebra B. So all open sets belong to this sigma algebra, and that we have a measure defined in this larger sigma algebra. I will say that mu is regular. So here's the definition of regular. If, well, for any set A in the sigma algebra F, and for any epsilon positive, I can find a closed set F, which is contained in the set A, which is contained in the set G, which is open. So F is contained in A, which is contained in G. F is closed. G is open, such that mu of G minus F is smaller than epsilon. Right? So we'll say that the measure is regular if any set in the sigma algebra F and for any epsilon, we can approximate the set A from below by a closed set, from above by an open set G, in such a way that the measure of G minus F is less than or equal to epsilon. Then let me do, before we continue, two remarks which are important. The first remark is that if you remember in the previous theorem, I assumed that the measure of A was finite. Note that here we are not assuming that the measure of A to be finite. Okay, so we did not assume that mu of A is finite. So in order for a measure to be regular, we have to approximate any set by open and closed sets. And then a second remark is that, well, here I assumed I required the measure of g minus f to be bounded by epsilon. We could as well require that the measure of g minus a to be smaller than epsilon, and the measure of a minus f to be smaller than epsilon, right? These two are equivalent because, well, it's clear that since g contains a and a contains f, once you know that g minus f has measure smaller than a, you obtain that these two measures are bounded by epsilon. And again, if you know that g minus a it's smaller than epsilon and a minus f has measure smaller than epsilon, since these two sets are disjoint, the measure of the union is bounded by 2 epsilon, but the union, it's exactly g minus f. So it's equivalent to require that this measure to be smaller than epsilon, or to require separately that these two sets to have measure less than or equal to a. So here's a third remark. So I assumed from the beginning that the sigma algebra generated by the open set, the Borel sigma algebra, was contained in F. Now I claim that if the measure mu is regular, then F is in fact contained in the completion of B with respect to mu. Right? So I want to show that any set in the sigma algebra F, it's contained in the completion of B with respect to mu. So let's fix a set A in F. And let's consider, so fix a sequence n. We can, since mu is regular, find open sets Gn which contain A, closed sets Fn which are contained in A. So Fn and Gn are open and closed sets and therefore belong to the sigma algebra B, and such that mu of Gn minus Fn to be smaller, say that, than 1 over n. Then of course if you take the union of Fn and the intersections of Gn, so let's consider F to be a union of Fn. So this is still an element of the sigma algebra B. Gn as the intersection, G, as the intersection of Gn, which is again an element of B. It's clear that F is contained in A, which is contained in G. And it's also clear that the measure of G minus F it's equal to 0. Right? Because, well, G, so the measure of G minus F, G, it's the intersection of Gn, so G is contained in Gn. So the measure of G minus F, it's certainly less than the measure of Gn minus F. But F is the union of Fn, so the union in K of Fk. This union certainly contains Fn, and therefore Gn minus this union, it's contained in Gn minus Fn, and this set has measure less than or equal to 1 over n. Therefore, since this is true for any n, the measure of G minus F has to be equal to 0. So up to this point, we obtain two sets, F and G, such that F it's contained in A it's contained in G, and the measure of G minus F it's equal to 0. So this is, I will erase everything I just said and just keep this information. So we, up to this point, obtained a set F, which is contained in A, contained in G. F and G belong to B, and the measure of G minus F it's equal to 0. Therefore, we can write A. So to show that A, our goal is to show that A belongs to the completion of B. Therefore, we have to write A as an element of B and a negligible set. But this is now very easy because A is contained in F, which belongs to B. So I can write A as F union A minus F. F belongs to the sigma algebra B because, well, we have seen that already. Now, A minus F, it's contained in G minus F because A, it's contained in G. And we have seen that the measure of G minus F is 0. Therefore, the set A minus F, it's contained in a set which has measure 0, which means that the set A minus F is negligible, and this proves that A belongs to the completion of B because we wrote A as the union of two sets, one of them in B and the other one which is negligible. So this proves that if a measure is regular, then the sigma algebra in which mu is defined, it's certainly contained in the completion of the Borelian sigma algebra, the completion of the sigma algebra generated by the open sets. The second theorem of this lecture states that the Lebesgue measure, which we constructed, is regular. So let me represent by mu the Lebesgue measure. So mu, remember, it's defined on the Lebesgue sigma algebra. And what we will prove is that mu is regular, which means that I just defined, so for any set A in the Lebesgue sigma algebra, I can find a set F which is contained in A and which is contained in G, F closed, G open, such that the measure of G minus F is less than or equal to epsilon. So this is what we need to prove. We have to fix an element of the Lebesgue sigma algebra, and we have to fix epsilon positive, and the goal is to find a closed set and an open set, closed set F and an open set G, such that the measure of G minus F is less than or equal to epsilon. And observe that we are not requiring here A to have finite measure. We have to show that, that we have to obtain these sets for any element A of the sigma algebra L. So let's prove this theorem. So let's fix an element A of the Lebesgue sigma algebra. Let's fix epsilon positive, and my goal will be to find an open set, so G open, and such that A, it's contained in G, and mu of G minus A smaller than epsilon. So this is the goal. And the idea of this proof will be very similar to the proof of the first theorem. But for that, we first need to replace A by a set of finite measure, and then in that theorem we covered A with elements of the algebra. At this point we will need to replace the elements of the algebra by open sets. So the first question is to replace A by sets of finite measure, and that's very easy. Let's represent by En the interval, say, minus nn. And let's denote by An the set A intersection En. So An is clearly an element of the Lebesgue sigma algebra. And now mu of An is bounded by 2n, so mu of An it's finite. And therefore we will be able to approximate An by elements of the algebra. So let me make that precise. Since this measure is finite, we know that there exists a sequence B and K, K greater or equal than 1, where each B and K belongs to the algebra, and An it's contained in the union of B and K. Moreover, for that fixed epsilon, since this measure is finite and the measure of An is given by an infimum, we can find these sets B and K in such a way that their measure almost approximate the measure of An in the following sense. Mu of An, so this is exactly what we did in the first theorem, in the proof of the first theorem. Mu of An, it's bounded by the sum K greater or equal than 1 of mu of B and K, plus, here instead of epsilon, I will use epsilon to the power 2n. I'm sorry, this is mu An, it's bounded by mu B and K, just because by definition of An, mu of An it's the infimum of all such sums, but we can find one specific covering of An which almost attain mu of An, so this is less than mu of An, and here is epsilon divided by 2n. Right? So we obtained here elements of the algebra which are covering the set An and whose measure is almost mu An. So it's bigger than mu N, but it's smaller than mu An plus epsilon to the 2n. Well, B and K are elements of the algebra. Right? So we don't want to cover An by unions of elements of the algebra, but we want to cover An by elements by open sets. So we need now to transform these sets which belong to the algebra in open sets. Well, if B and K belongs to the algebra, we know that B and K, we know which are the elements of the algebra. The elements of the algebra are finite unions, disjoint unions of elements of the semi-algebra, which in our case are intervals. Since An is contained in minus nn, we can assume that all these sets B and K are also contained in minus nn, which means that they are finite disjoint unions or of intervals which are bounded. So B and K can be written as a sum from 1, say, to number L, which depends on n and k, of, let me represent by I, n, k, j. These are bounded intervals, so they are all of the form I, A, n, k, j, b, n, k, j. Right? This, by definition of, because we know that the elements of the algebra are formed by finite unions of elements of the semi-algebra, and the elements of the semi-algebra which are bounded are all intervals of this type. So let me add, so this set, it's clearly bounded by G and K. So I want to transform these sets into open sets, and for that I will just increase a little bit the right hand. So I replace B and J by B, N, K, J plus some delta which depends on N, K, J, which is strictly positive. And so let me denote to make it very clear. Let me denote by CNKJ the point B N K J plus some delta N K J, which are all positives. So these delta N K J are positive, and they are very small, and we'll see later what how small they are. So let me call the set G, J, N, K, J, the open interval A, N, K, J, C, N, K, J. So it's clear that B and K, it's contained in G and K, which is equal. So by this is the definition of G and K. It's the, now these intervals A, C may not be disjoint. So this will be a union from J from 1 up to L and K of the intervals, the open intervals G, J, and K, J. And so let me write it here. The measure of G, N, K, which is G and K is this union, so by subadditivity, this measure is smaller or equal than the sum from J from 1 up to L and K of the measure of J and Kj. The measure of J and Kj, it's the measure of this interval, but the measure of this interval, it's exactly the measure of this interval plus delta and Kj. So this is less than the measure of I and Kj plus delta and Kj. So now I will choose these deltas in such a way that the sum of these deltas is bounded. So the sum of these deltas, it's bounded by epsilon divided by 2n divided by 2 to the power k. Right, so I'll choose this delta very, very small in such a way that this finite sum of this delta, it's bounded by this quantity. And now remember that the measure of these intervals are disjoint. So the sum of this measure, it's the measure of the sum, and the measure of the sum, it's the measure of B and K. So the sum of these measures, it's exactly the measure of B and K. So what we have here is the measure of B and K plus epsilon divided by 2 to the power n, 2 to the power k. So we just proved that. So what did we do? We construct open sets, right? Because G and K is the union of open intervals, so it's an open set. So we constructed open sets represented by G and K such that they contain B and K, but the measure of these sets, it's bounded by the measure of B and K plus epsilon to the power 2n plus k. So I'm just erasing everything I wrote about B and K and G and K, just conserving the important properties of G and K, so that G and K, it's an open set, contains B and K, and the measure of G and K, it's bounded by the measure of B and K plus epsilon to the power 2n plus k. So let me erase everything. And let me write that again here. So B and K, it's contained in G and K. G and K, it's an open set. And the measure of G and K is less than or equal to the measure of B and K plus epsilon divided by 2n to the power k. Right, so this is what we just proved. Right, now my first observation is that, well, since I erased, but since an, I shouldn't have erased, but I erased it, since an is contained in the union of B and K, right? So this was one of the properties of B and K. B and K were elements of the algebra, and their union contained an. Well, since B and K is contained in G and K, it's also true that an is contained in the union of G and K. And let me call that set Gn, which is also an open set, because each of these sets is an open set, and we know that union of open sets is an open set. So an is contained in Gn. And on the other hand, we have that the measure of G and K, it's bounded by the measure of B and K plus. So let me write this inequality, that if I take the sum of G and K, right? So let's sum over K the measure of the set G and K. Since the measure of G and K is bounded by the measure of B and K plus epsilon to the power divided by 2 to the power n to the power k, this is bounded by the sum of the measure of B and K plus the sum of this expression in K. But the sum in K, it's exactly epsilon to the power 2n. And now let's use the property of B and K. The sum of the measure of B and K, it's bounded by the measure of an plus epsilon to the power 2n. So this is less than or equal to the measure of an. So there is one epsilon over 2n and another one, so there is 2 epsilon 2n. And of course, Gn, which is the union of G and K, the measure of Gn, it's bounded by the sum, by subadditivity, the measure of Gn, it's bounded by the sum of the measures of G and K. So this is greater or equal than the measure of Gn. So in conclusion, we obtained up to now an open set Gn, which contains an, but whose measure, it's bounded by the measure of an plus 2 epsilon divided by 2n. So at this point, I can erase everything but the definition of an. So bn will not be used anymore. Let me just recall what we obtain here. We obtain a set an, which is contained in a set Gn, which is open. Right? And the measure of Gn is less than or equal to the measure of an plus 2 epsilon divided by 2 to the power n. Now we are essentially done. So let's define G to be the union of Gn, right? G, it's an open set. Let's observe that an, it's given as A intersection En. So A, it's certainly equal to the union of an, by definition of an. Since an is contained in Gn, it's clear that A is contained in G. Right? Each set an is contained in Gn, therefore the union is contained in the union of G. And the measure of G minus A, which is what we wanted to estimate. So remember, we obtained already the set G, which is open. It contains A. So now we have to estimate the measure of G minus A. So the measure of G minus A, by definition, it's this is equal to the measure of the union of Gn minus the union of an. If you don't want to mix indices, let's call that union of ak. Well, I leave it to you to check that the union of Jn minus the union of ak, it's contained in the union of Gn minus an. Right? Any point which is in the union of Gn and it's not in the union of ak, it's in one of the Gn and not in the same an. So since this set is contained in that one, the measure of this set it's less than or equal to the measure of this set. And by subadditivity, the measure of this set is less than or equal than the measure of Gn minus an. But the measure of Gn minus an, since Gn contains an and the measure of an is finite, this is the measure of Gn minus the measure of an. And the measure of Jn minus the measure of En, it's bounded by 2 epsilon to the power 2n, so if you sum over n, you get that this is bounded by 2 epsilon as required. So this concludes the proof that for any set A which is Lebesgue measurable, for any epsilon, we can find an open set G which contains A, and for which the measure of G minus A is less than or equal to epsilon. So this concludes the first part of the proof. So let me now, because we still have to find a closed set, but that will be very easy. We'll just go by complements. Right? So now we need to find a closed set F such that F is contained in A and the measure of A minus F is less than or equal to epsilon. But that's very easy because we'll just take the complement of A. So let's take the complement of A. By the first part of the proof, we can find an open set. So let's call H an open set, such that the measure of H minus A is less than or equal to epsilon. Right? By the first part of the proof, for A complement, we can find an open set H, which contains A complement, and such that the measure of H minus A is less than epsilon. Well, now let's take F as H complement. So since H, it's an open set, H complement, it's a closed set. Let's take complements in this inequality, this relation. So this relation tells you that H complement is contained in A, but H complement it's F. So F, it's a closed set which is indeed contained in A, and the measure of A minus F, well, this is the measure, well, it's clear it's H minus A, but let's show it. So A minus F, it's A intersection F complement. Well, F complement, it's I'm sorry, here it's complement, right? What we can obtain, it's a set H, which is open, which contains A complement, and the measure of H minus A complement is smaller than epsilon. So there was a mistake here. It's A complement and not A. So let's continue here. A minus F, it's A intersection F complement. F complement, it's H. So this is nu of A intersection H. And we can, A can be written as A complement complement, and therefore H intersection A can be written as H minus A complement, and this is bounded by epsilon. So this proves that A minus F, the measure of A minus F, it's indeed bounded by epsilon, and concludes the proof of the second theorem of this lecture. So here's the theorem we just proved. We have proved that the Lebesgue measure is regular. Now just a remark to conclude this lecture. So we can approximate any Lebesgue measurable set by open and closed sets. So now we will take intersection of open sets, union of closed sets, in order to approximate A exactly. So remember that we call a set F sigma. So F sigmas are the class of sets which can be obtained as countable union of closed sets. So these are countable union of closed sets. And the same way we call G delta countable intersections of open sets. So by taking here intersections of open sets and union of closed sets, we can approximate a set A exactly. So my claim is that for any A, which is Lebesgue measurable, we can find, well, one set which is in F sigma. So let me call this set in F sigma B or R, which is F sigma. And let me call S a set which is in G delta, such that R, it's contained in A, which is contained in C. So how we do that, and such that the measure of S minus R, it's equal to 0. Right. So we can approximate any set which is Lebesgue measurable by well, F sigma sets and G delta sets. G delta which contains and F sigma which is contained. And how do we do that? Well, we use this argument many times here. We know that for any epsilon we can find an open and closed sets. So now takes a sequence of epsilons, say epsilon equal to 1 over n. For each n you find an open set Gn and a closed set Fn. Take the intersections of Gn and call that set S. Take the union of the sets Fn and call that R. So R is certainly an F sigma, it's the union of closed sets. S is a G delta, it's the intersection of open sets. S clearly contains A, and A contains R. And the measure of S minus R, it's bounded by the measure of Gn minus Fn for any n, which is bounded by 1 over n. And from that you conclude that the measure of S minus R is equal to 0. So, well, this concludes the remark, so let me just stress once again, if you want to approximate by epsilon, you can approximate by either closed sets or open sets. But if you want an exact approximation, then you have to go to F sigmas or G delta sets. And this is the main result of this lecture.